We have just learned that to solve an exponential equation that already has like bases, we simply set the exponents equal. But what if we have an exponential equation for which we cannot obtain like bases? Notice on this example, 3 and 7 neither can be written as a power of a common base. So how do we solve an equation like this? Well, before I answer that question, let me ask you another question. How do we solve a simple equation like this? Well, we use the principle of inverse operations. In this very simple linear equation, our goal is to isolate x. But how do we isolate x? Well, you probably know the first thing we do here is subtract 1 from both sides. But why do we subtract 1? Well, we subtract 1 because it's the opposite of addition. Addition and subtraction are inverse operations. That is, they cancel each other out. Working a little further, the next step would clearly be to divide both sides by 2. But why do we divide both sides by 2? We divide both sides by 2 because we're undoing the multiplication that's applied to the x. Division and multiplication are inverse functions. So that allows us to solve the equation. This principle of applying inverse operations goes for any type of equation, including exponential equations. So if we have the case where we have an exponential equation where we cannot get like bases, we're going to use the inverse operation. Hopefully you know by now that logarithms and exponential functions are inverses or opposite operations. Exponentials and logarithms have the same relationship as addition and subtraction or multiplication and division. So that's the key. If we cannot get like bases, we're going to use logarithms to solve the equation. So let's recall that the expression x equals a to the y is equivalent to y equals log base a of x. So if I have an equation in exponential form, my goal is to rewrite it in logarithmic form. So reminders of the important points on how to do that. The base of my exponential equation is the base of the logarithm. The exponent in the exponential equation is what's isolated in a logarithm. Remember, a logarithm represents an exponent, and the result of our exponential evaluation becomes the argument of the logarithm. So essentially, we're just going to rearrange an exponential equation in logarithmic form. That's going to isolate the exponent and solve the equation. So again, here's the procedure. If it is impossible to express both sides of an exponential equation as a power of a common base, do the following. Number 1, isolate the exponential term. Number 2, convert to logarithmic form. Essentially, you're using an inverse operation there to isolate the exponent. Number 3, if necessary, isolate the variable, and then as always, number 4, check by substitution. So let's give this a try on example 2. Find the exact solution to the following exponential equations. Then approximate the solution to the nearest hundredth, that'll be 2 decimal places, using our calculator. So on example A, we have 3 to the x plus 1 equals 7. Now the base on the left side is 3 and the base on the right side is 7. Both of those numbers are prime numbers, and they cannot be written as a power of a common base. So we're going to use logarithms to solve. All we have to do is rewrite the exponential equation in logarithmic form. So we'll begin our logarithm and identify the base of the exponential, which is 3. That becomes the base of our logarithm. Remember, the argument of the logarithm is the result of the exponential evaluation, and the logarithm spits out or isolates the exponent. So now to solve the equation, all I have to do is isolate x, and we can easily do that by subtracting 1 from both sides. Now I'm going to rewrite this. X equals log base 3 of 7 minus 1. This is what we call the exact solution. But what value does that exact expression actually represent? Well, let's use our calculator to approximate this value so we can wrap our minds around what kind of number that is. Recall the key combination for typing in a logarithm is math alpha math. We can type in log base 3 of 7 minus 1. So the approximate value of our solution to the nearest hundredth or 2 decimal places is 0.77. This is what we call the approximate solution. Now, let's see what happens when we check our original equation with the exact solution and with the approximate solution. So I'm going to begin with the exact solution. So we want to take log base 3 of 7 minus 1 and plug it into the original equation for x. So we're going to evaluate 3 raised to the power. Remember the combo math, alpha, math to get our logarithm in there. Log base 3 of 7 minus 1 outside parentheses. And don't forget, in the original equation, we had a plus 1 in the exponent. So we plugged in our x. Now we're going to finish out the exponent. And notice that gives me a perfect balance between the left and right sides of the equation. Now compare that to when we plug in the approximate solution. So I'm going to replace x this time with 0.77. So we have 3 raised to the 0.77 plus 1. And notice it gives me approximately 7, but not a perfectly balanced equation. So when we have a little bit of rounding error associated with our solution, it gives us a little bit of rounding error associated with our solution. But you can see that both sides are so close that that gives you confidence that at least you have the correct approximate solution. Okay, let's try example B. We have 6 to the 3x minus 5 equals 13. So the base on the left is 6 and the base on the right is 13. There's no common base between 6 and 13. So we're going to rewrite this in logarithmic form. So we'll introduce our logarithm. The base of the logarithm is the base of our exponential expression, which is 6. The argument of the logarithm is the result of that exponential evaluation. And the logarithm isolates the exponent. So now we need to solve for x. We can begin by adding 5 to both sides. So we have log base 6 of 13 plus 5 equals 3x. And then we're going to solve by dividing both sides by 3. And I'm going to divide the entire left side by 3. So we end up with, and I'm going to switch around here, x equals log base 6 of 13 plus 5, all divided by 3. This would be our exact solution. Let's go ahead and use our calculator to approximate this value. So I'm going to begin with a big fraction, alpha y equals number 1, and then the combo math, alpha, math to type in our logarithm. Log base 6 of 13 plus 5 on the top, and we are dividing by 3 on the bottom. So this gives us the approximate value, 2.14. Now, let me remind you of a technique that you can use to check your solutions. So right now, I'm going to type second enter. That's going to recall the logarithm that I just typed in, just saves me a little bit of work. Remember, on the left side of your calculator here, you have an STO store button. So I'm going to store that exact solution under alpha A. Now, remember, it's going to give me the decimal approximation, but it's going to store the exact value under A. So now, to check with my exact solution, I just have to type in A for x. So we're going to evaluate 6 to the alpha A minus 5, and we can see that gives us a perfect balance. Whereas, if we evaluate 6 to the 3 times our approximate solution, 2.14, minus 5, we'll get approximately 13. But either way, we can be confident that we have the correct solution. Now, if our equation has base e, like what you see here on our third example, we have to remember when we convert to logarithmic form, the special notation for that natural base. With the natural base e, we write the logarithm as ln or natural log. Also remember that natural log is automatically base e, so I don't have to write the subscript to represent the base here. So when we rewrite this in logarithmic form, we end up with natural log of 200 equals exponent x squared. Now, on the previous two examples, when we converted to logarithmic form, the resulting equation was a linear equation. That is, we could solve by isolating x. But in this case, we have a quadratic equation. But as you know, we can solve quadratic equations in this form simply by taking the square root of both sides, as long as we don't forget that plus or minus. So switching sides here, the square root of x squared is x, so we come up with two possible solutions, plus or minus natural log of 200. So we've got two exact solutions. Let's use our calculator to approximate these solutions. So we're going to type in square root of natural log of 200. We have two functions composed or embedded here. So our approximate solution to the nearest hundredth would be 2.30. And don't forget, we've got two possibilities, plus or minus 2.30. And I'm just going to quickly check this with the approximate value. So let's evaluate e raised to the 2.30 squared. And notice we have 198. That's approximately 200. Now, here's what it would look like with the exact solution. We have e, second e, raised to the square root. Let me put that in parentheses here. Square root, natural log 200. I'm going to close the argument, close that exponent and square it. And I feel better about that one, exactly 200. Also, because when you square a negative, you get a positive, we know our negative solution is correct as well. So if you cannot get like bases, simply convert your entire equation to logarithmic form and then solve the resulting equation.